And I'm Hugh Ross. I have had a doctoral degree in astrophysics. I've also been a pastor for the past 47 years, so I come with a two books perspective on this. But what I'm going to be sharing with you this afternoon is a brand new talk, literally based on a discovery that was published just a few days ago, although the heart of it is based on a discovery that goes back a year ago. So, and this first slide just simply shows you that our organization, Reasons to Believe, we have a 24/7 YouTube channel. You can subscribe to that for free. There's literally over 10,000 video clips there that you can watch. And all of our scholars at Reasons to Believe do take questions on Facebook and Twitter. We don't promise to answer them all, but we try to get to as many as we possibly can. So if you don't get to ask a question today, and I'm going to try to leave time for Q&A. And if you get this QR code with your smartphone, you will get a free copy of the book that my wife and I wrote, Always Be Ready. So you take that to our little desk out there, and you can get a free copy of that book. But the talk is based on the origin of the elements. And I'm sure that all of you have been exposed to the periodic table when you went to public school or private school, but probably your science teachers didn't tell you what a miracle that periodic table is. And we're probably living on the only planet that has all those elements present and available for us to use. 92 elements in the periodic table, and they're all here on planet Earth, but you're not going to find them anywhere else. Now, a question I get asked a lot is, well, maybe I could ask you this. Have you ever been asked this question? If God wanted humans, why are there so many useless stars and galaxies? How many have ever had that question posed to you? Okay, quite a few of you. Why are there 200 billion useless galaxies where each of them has 300 billion stars? I mean, that's a lot of stars that are sitting out there. And if God wanted life, all he needs is one star and one planet, a moon. Why all this other stuff? Well, the answer is that the universe's mass determines what elements you get in the universe. And, we live in a Big Bang universe. The Bible, by the way, predicted Big Bang cosmology thousands of years before any astronomer discovered it. You'll find it many places in the Old Testament, the four fundamental features of Big Bang cosmology, that the universe has an origin, a beginning, and a beginning that includes the beginning of space and time itself, and how the universe expands from that cosmic beginning. 11 different passages written by 6 different Old Testament authors speak about the expansion of the universe and how it expands under laws of physics that do not change, where one of those laws is a pervasive law of decay. But in an expanding universe, the mass of the universe determines how much of the primordial hydrogen is fused into helium. The universe begins with only one element, the element hydrogen. But the universe starts off infinitesimally small and nearly infinitely hot. But as it expands, it cools. It's the same principle of your car engine. When the piston chamber expands, the gasoline stops burning because it cools down. Well, likewise, the universe gets colder and colder as it continues to expand. And during the first 3.5 minutes of the existence of the universe, it passes through a 20-second long window where hydrogen can fuse into helium, roughly the temperature between 150 billion and 17 billion degrees Celsius. That's the temperature range where hydrogen can fuse into helium. And the greater the mass, the longer it takes for the universe to go through that temperature window. So, for example, if you were to make the universe slightly less massive than what it is, the universe would expand so rapidly throughout that temperature window that only a small amount of the primordial hydrogen would be fused into helium. And the future stars would not be able to make any elements heavier than helium. In which case, this is what the periodic table would look like. You'd have hydrogen, you'd have a little bit of helium, and nothing else. Now, that would be really good news for all of you students of chemistry, because that would make a chemistry class really easy to pass. You'd only have 3 possible compounds in the history of the universe, but there'd be no possibility for life. Because if all you've got is hydrogen and helium, you're missing the key elements that life requires. On the other hand, if you were to make the universe slightly more massive than what it is, more massive than what you would get with those 200 billion galaxies, the universe would spend so much time in that temperature window that the universe would wind up fusing a lot more of the primordial hydrogen to helium. And what that would do is that the future stars, in a very astronomically short period of time, would take all of that hydrogen and helium and fuse it into nothing but elements heavier than manganese. Everything would be iron or heavier. And this is what the periodic table would look like. You'd have iron, you'd have all the elements heavier than iron, but you'd have no elements lighter than iron. And guess what? You'd be missing the carbon, the oxygen, the nitrogen, the phosphorus, the potassium that you need to make life possible. So unless we fine-tune to an extraordinary degree the mass of the universe, you either get a periodic table with only hydrogen and helium, or you get a periodic table where everything is iron or heavier. And in both cases, life is not possible. Now you say, well, to what degree do we have to fine-tune the mass of the universe in order to get the full periodic table as a possibility on a planet? You'd have to fine-tune it to within 1 part in a quadrillion, 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 quadrillion. 1 part in 10 to the 60th. And to put that in context, the very best example of human engineering inventiveness and achievement, it is a level of about 1 part in 10 to the 29. So we're looking at something that's 10 to the 31 times more fine-tuned than anything we human beings are capable of, which tells us someone a lot more intelligent and knowledgeable and more powerful than us must have been the one that designed the universe so that we can get a periodic table that looks like this, the one that you studied when you took chemistry in an elementary public school classroom. And you actually wind up with the key 3 elements that life needs, the carbon, the nitrogen, and the oxygen. But we actually need the intervention of the supernatural, super intelligent creator to get the carbon, the nitrogen, and the oxygen. And what we discover is that there's a fundamental barrier. You start off with just hydrogen and helium, and then we got the stars that have this very hot nuclear furnace in the core, but you really get nothing past helium except for an extraordinary fine-tuned situation. And that's because helium's ground state energy level, if you put 2 helium atoms together, it adds up to beryllium. And so you have the ground state energy level of beryllium being equal to that of a helium atom plus a helium atom. If that wasn't the case, stars would not be able to fuse anything beyond helium. But because the helium ground state energy level is exactly 1/2 of what you got for beryllium, there's a pathway whereby you can get the synthesis of helium to make beryllium. And so how does that help you for carbon and nitrogen and oxygen? This is how it helps. Because the ground state energy level of the beryllium plus the ground state energy level of the helium almost exactly adds up to the excited state energy level of carbon. And if that was the case, you could have a universe with helium and hydrogen and beryllium, but no carbon, no oxygen, no nitrogen. But because of this very delicate fine-tuned balance, it's possible that you can fuse beryllium and helium and actually get carbon. Now, it was a team of astrophysicists at Caltech back in 1956, Jeffrey and Margaret Burbidge, Willie Fowler, and Fred Hoyle, who got together, and their paper to this very day ranks as the most cited physics paper in all of physics literature. And what they did is they figured out, well, if we got carbon, how do we get oxygen? Because what they found out is, okay, it's possible that we could get carbon and you add a helium and you get oxygen, but the problem is you'd wind up with a universe with a whole lot of oxygen and no carbon. Or you wind up with a universe with a lot of carbon and no oxygen. And for life, we need both carbon and oxygen. And what they discovered back in 1956 is that the ground state energy level of carbon and oxygen are almost the same. And because they're almost the same, you get a universe that is roughly equal amounts of carbon and oxygen, although not quite. Notice that the ground state energy level of the oxygen is a little bit less than the carbon. And so you wind up with a universe with a little more oxygen than it has carbon. That is crucial for life. If it was the other way around, we wouldn't be here. It's necessary that you have more oxygen than that you have carbon, because oxygen reacts very powerfully with other elements, and that basically fills out this amazing array. This is what makes chemistry classes hard to pass, the fact that oxygen reacts with almost everything. And that's because its ground state energy level is slightly less than carbon, so you wind up with a universe with the just right amounts of carbon and oxygen. And Fred Hoyle, one of the 4 authors of this most cited paper, he wrote in an engineering journal later in his life, and this is what he said about this balance. He says, a common sense interpretation of the facts suggests that a super intellect has monkeyed with the physics as well as with the chemistry and biology, and that there are no blind forces worth speaking about in nature. The numbers one calculates from the facts seem to me so overwhelming as to put this conclusion beyond question. Now, when I was 7 years of age, I read one of Fred Hoyle's books, The Nature of the Universe. 2 entire chapters of that book, he's blistering attack on the Christian faith and the Bible. To his dying day, he rejected the Bible. He rejected the God of the Bible. But nevertheless, because of the force of the fine-tuning, he saw what's necessary to get a universe with approximately equal amounts of carbon and oxygen, where oxygen is a little more abundant than carbon. He says, this isn't pure naturalism. There's something going on. He says, I don't think it's a God of the Bible, but it's a God of some sort that's behind all of this. And so this explains why we have this periodic table. But to get this periodic table, you're not going to get it with one generation of stars. You need 3 separate generations of stars. It explains why, to have human beings in the universe, we have to take about almost 14 billion years of cosmic history. It takes that long to get this periodic table in place. And so in astronomy, we speak about the firstborn stars as population 3 stars. And these population 3 stars take the primordial hydrogen and helium, and they make small amounts of carbon, oxygen, nitrogen, and iron. But when the bigger of these stars explode, they basically splatter into interstellar space the ashes of their nuclear burning. And the second generation of stars, the population 2 stars, take those ashes, and now you've got stars, not just with hydrogen and helium, but you've got hydrogen, helium, carbon, nitrogen, oxygen, iron. And with that richer mix, when the larger of those stars go through their nuclear burning cycle and explode and splatter ashes into interstellar space, those ashes have a much higher enrichment of metals, of elements heavier than helium than the first generation stars. We orbit a 3rd generation star. So our star, the sun, formed after the 2nd generation stars. But it had the benefit of forming out of the enriched ashes from the explosion of these population 2 stars. And this explains why a planet orbiting a population 3 star can have this full panoply of elements, whereas planets orbiting population 2 stars cannot. They'll have some, but they will not have all. Now, what I'm going to be sharing with you in the rest of this talk are some recent discoveries in astrophysics that basically make the point not any population, one star, is going to have the full complement of these elements. Matter of fact, we may be the only planet in the universe that has the full complement. In fact, we know for certain we're the only planet in the universe that has a superabundance of elements heavier than iron. It's one thing to have planets orbiting a star where you got elements lighter than iron, and you will have elements heavier than iron, but in order to sustain the advanced civilization and technology that we humans have been able to achieve here on planet Earth, you not only need elements heavier than iron, you need a superabundance of them. And so that's what I'm going to be sharing with you, how it was that our planet Earth wound up with a superabundance of elements heavier than iron. Now, if we look at the elements heavier than iron, what we discover is about half of them form through slow neutron capture. The rest of them form through what's called rapid neutron capture. And we say, what do you mean by that? Well, you have, say, elements like manganese and iron, and if you shower neutrons upon them, those neutrons will stick, and you wind up with the heavier elements. And you can get about half of these elements with slow-moving neutrons, impacting the iron, the manganese, and things like sodium. But in order to get half of these elements, you need very rapid-moving neutrons. And it's not just enough to have fast-moving neutrons, you need them in great concentration. And so I remember when I was a graduate student at the University of Toronto and doing research at Caltech there afterwards, that we astronomers were saying, well, the only place where you keep these really fast-moving neutrons is supernova explosions. So in the textbooks, that's basically what they tell you, that these rapid process elements came from the explosions of supernovas. And the bigger the supernova, the more neutrons you get and the faster the neutrons move. But what became evident about 3 years ago is that supernovae are not going to do the job. They can explain how you get all these elements, but they are not able to explain how you get them in the abundance we see here on planet Earth. And so, yeah, they would all be rare elements at low abundance levels, so low of an abundance level that not only would our civilization be possible, but we human beings would be impossible. Why? Because a lot of these elements are present in our human bodies. And if you don't have them in sufficient abundance, you will die. Now, one of the big technological achievements of the last several years is the building of gravity wave telescopes. I mean, you've probably heard of optical telescopes, radio telescopes, infrared telescopes, gamma ray telescopes. Several years ago, when they began to recognize where do all these things come from, they realized, okay, it's going to have some sort of explanation in high gravitational concentration events. And so that's when your tax dollars are beginning to be devoted to the building of gravity wave telescopes. We have one in the state of Washington, they got one in the state of Louisiana, and they got a third one in Pisa, Italy. It's the LIGO instrument. And what it is, it's an interferometer where they have two mirrors separated by 4 kilometers. And basically they shine a laser beam from one mirror to the other, and they measure the time that it takes to go from one mirror to the other. It's extremely well designed. In fact, this ranks as the best designed machine we humans have ever built. So how sensitive is it? They can detect a distance difference by that laser beam going down that 4 kilometers and coming back to within 1/10 the diameter of a proton. That's how sensitive it is. Now you say, why did they have to build several? Well, when an ocean wave crashes on the Washington beach, it will disturb the separation of the two mirrors by a lot more than 1/10 the diameter of a proton. And so every wave that crashes on the beach generates a signal. Now, also, if a truck goes by 50 miles away, it will generate a signal. So what they did is said, well, we're going to put one in Louisiana in a different geographical area with different geology, and the truck that goes by at the Washington gravitational telescope is not going to impact the one in Louisiana. And likewise, they put one in Italy. So yeah, there's ocean waves, there's trucks, there's cars, there's cows running around in the field nearby that disturb the distance between the mirrors, but it's not going to be the same at all three sites. If they see the same signal at all three sites, they know it's from somewhere beyond our solar system. And by having three, they can actually figure out where the signal is coming from. And so you may have heard that this LIGO instrument detected the merger event of two black holes. Two black holes orbiting one another, and as they orbit one another, they lose gravitational energy, and then they merge. And when they merge, there's a tremendous outburst of gravitational waves. And that's what this telescope picked up. So here's an example of what's happening here, is you get two black holes orbiting one another. They lose gravitational energy, so they spiral in towards one another, and they get quite close to one another, and then you really begin to see a burst of gravitational energy, and then they merge, and they become a bigger black hole. The first event that was observed, they noticed that there were two black holes that were approximately the same mass, and the total mass was about 63 times the mass of the sun. But when they merged, they discovered that it was only 60 times the mass of the sun. Three solar masses were radiated as gravitational energy. And that was sufficiently strong to be picked up by the telescope. So here we got the two black holes orbiting one another. They're getting close to merging together, and then they merge. And this is what it looks like when you're at the gravitational wave telescope. As they begin to get closer and closer together as they're orbiting, you see these waves, and then you get this big spike when they finally merge. And then when they do merge and form a bigger black hole, the gravitational waves dissipate away. And so here's another example of what's happening here, and you can see the merging take place. Well, what happened a little less than 2 years ago is they actually were able to use the same instruments to observe the merging of two neutron stars. And so two neutron stars were orbiting one another. They merge and they form a black hole. Now, this was different and a big breakthrough because when two black holes orbit one another and merge, there's no electromagnetic radiation. I mean, black holes, by definition, trap everything that comes close enough to it, and we call them black for that region. They don't radiate. But neutron stars are not as massive as black holes. So when they orbit one another and come into a merger, there's a huge blast, not only of gravitational waves, but infrared waves. We can see optical waves, radio waves. And when this first merger took place, what they could see is, hey, we're getting really close to this thing merging together. They alerted observatories around the world. And so 9,000 astronomers were able to observe the merging event at all these different wavelengths. And a whole entire journal issue was devoted to publishing their results. And they were able to actually measure the spectral lines. And by this means, they're able to determine what elements were produced, because when these two neutron stars are merging together, I mean, these neutron stars are pure neutrons. A neutron star is a solid crystal of neutrons packed together where the neutrons are actually touching one another. And so when they merge, the neutrons all get disturbed, and so you have this huge density of very fast-moving neutrons. Bottom line, what they discovered is that the supernova do make a few of these rapid process neutron elements, but that these neutron star merging events make way more. In fact, we now realize of these heavy elements in the crust of the Earth, at least 95% of them came from neutron star merging events. Now, neutron star merging events are exceptionally rare. But before I get into that, there was a major breakthrough that came through the very first discovery of a neutron star merging event. We've now seen two. First one happened about 18, 19 months ago. And the second one happened just a couple of months ago. They've now observed two of them. But those two sets of observations basically proved what's called Lorentz invariance. Now, I could spend the rest of my time here discussing the technical details of what this means, but I'm not going to give you a physics lecture here, okay? I'm going to give you the bottom line. The bottom line is that these two observations proved that Lorentz invariance was verified to better than a factor of 2 to any previous observation or experiment. So what does that mean, bottom line? It means that the laws of physics are identical to all observers at all time and throughout the entire geography of the universe. And this is significant because 7 places in the Bible it either directly states or implies the laws of physics do not change. Probably the most famous text is Jeremiah 33, where God says to the Jews, "You change your mind all the time, but I'm a God that doesn't change. I'm immutable. As proof, look to the laws that govern the heavens and the earth. As they never change, I never change." But now we have direct scientific proof that what the Bible stated thousands of years ago indeed is correct. So this is evidence that the Bible has predictive power, the power to accurately predict future scientific discoveries and to do so to an amazing degree. Now, I was also very much personally encouraged by these neutron star merging events because one of the published results was this statement in the paper published by Vitali et al. In the journal Science. And he says, as a result of these 2 neutron star merging events, we can now definitively state that there is no evidence of black hole mimickers, which means there is no evidence that there are exotic objects that mimic the characteristics of black holes, such as boson stars, soliton stars, or neutrino balls. And I got a paper published in the peer-reviewed literature about a year and a month ago now. And the title of the paper is Black Holes as Evidence of God's Care. And I drew 3 atheist physicists as reviewers. And what's exciting about this paper, the entire paper is free for anyone to read, but they also published the reviews of the reviewers and my responses to the reviewers. Well, you can read those reviews. They're available free online. All you got to do is put black holes as evidence of God's care. The paper will pop right up, and you'll be able to see the paper plus the reviews. But what the atheist theoretical physicists were saying is, Dr. Ross, you actually believe that black holes are real. Maybe they're not. Maybe they're soliton stars. Maybe they're boson stars. And said, we want your paper to be rejected because we think your paper is based on the false premise that black holes are real. Well, you can read my response. It was actually before these discoveries where I said, well, I've done a survey of the scientific literature. You know, there's 26,000 papers published on black holes. There's only 8 papers published on soliton stars and boson stars. And I read those papers carefully and said, the reason why there's only 8 of these papers published is that none of these theoretical physicists are able to explain how any of these stars can be stable for more than a few minutes. So, and we know these objects that we call black holes have been around a long time and they're stable. So that explains why we see 26,000 papers. Anyway, the bottom line is he finally conceded and says, okay, I'll let the paper get published. But now we know for certain these kinds of objects cannot possibly exist. But the bigger role they play is they explain why we get such a superabundance of these heavy elements on Earth. Now, I mentioned you get a small amount from supernova, but we now are thinking supernova account for maybe at most 2 or 3% of these R-process heavy elements we see here on planet Earth. However, a paper got published about a week and a half ago making the point that we not only have supernova exploding, we have an extremely rare event called a hypernova. Now, what you see here with a supernova, for about a 2-month window, it shines with as much light as an entire galaxy. But I'm going to show you an example of a hypernova. Okay, you can see the galaxy in the background. This is a very distant galaxy. And so that's really a giant galaxy you see there. But notice the arrow pointing to the hypernova. In this case, the star is showing a light emission that's more than 100 times greater than the entire galaxy in which it formed. And what happened about 10 days ago, as I said, this solves the problem of where molybdenum comes from. Because these neutron star merging events cannot make molybdenum. The supernova cannot make molybdenum. It's the hypernova that makes molybdenum. And planet Earth has 5 times as much molybdenum as what we see in the rest of the universe, meaning that our planet must have formed adjacent to a hypernova to explain why we have molybdenum. Now, many of you may not really remember molybdenum from your junior high science physics class, but molybdenum is what we call a vital poison. There's molybdenum in your body, and if you're molybdenum deficient, you'll get sick and you'll die. And if you got too much molybdenum in your body, it'll be toxic and you'll also die. And incidentally, there are 22 elements in the periodic table that are vital poisons. Too little in your diet, you die. Too much in your diet, you die. They have to be fine-tuned. And I'm going to end my talk by actually showing you a list of these vital poisons, where you are living on the only planetary body to a very high probability that has these vital poisons at the just right levels so that you can live and thrive. And it's we humans that have the greatest number of vital poison elements in our body. So yes, it's the hypernova that we now know is responsible for the molybdenum. So the molybdenum problem got solved just 10 days ago. Where do we get our molybdenum from? Aren't you glad you came to this conference to hear about the latest stuff? Okay. But to make all this possible, we now realize that our solar system had to have formed in a giant open cluster of stars. Astronomers calculate there had to be a minimum of 10,000 stars packed close together in this star cluster in which our star, the sun, was formed. And it had to be a star cluster sufficiently big and sufficiently dense that we would be exposed to a neutron star merging event. So somewhere within this, and incidentally, this has to be fine-tuned. If you're too close to the neutron star merging event, your solar system gets disintegrated, so we'll be blasted away. But if you're too far away, you won't get enough enrichment of these elements that are heavier than iron. So you got to be just the right distance and at just the right time. It has to be happening at the time that our solar system is forming. That's when the enrichment takes place. But also, we have to be adjacent to 3 different kinds of supernova eruptions in order to get, because one kind of supernova makes one set of elements, another one makes another. And again, it has to be fine-tuned. You can't be too close to these supernova, otherwise our solar system gets destroyed. And you can't be too far away, otherwise you get inadequate enrichment. And we need fluorine in order to have strong teeth. By the way, you need molybdenum to have strong teeth too. Molybdenum is a key component. And I'll just give you a little sidetrack here. Another advantage to breastfeeding over bottle feeding, if you bottle feed your infant, there's not enough molybdenum in the, and by the way, for infants, they don't need as much molybdenum as we adults do, so you can kind of get away with it. But because of this paper was published 10 days ago, the next generation of baby formula, they're going to put molybdenum in it. Because of now they didn't think, well, okay. So physics journal papers actually have a significance for your health. Okay. But as these stars continue to form, you actually have stars forming quickly, burning up quickly, and they become what are called asymptotic giant branch stars. That's where most of your fluorine comes from. So again, our planetary system has to form adjacent to what, I'm not going into the details, but it's an asymptotic giant branch star that radiates out all the fluorine we need, and now we know we have to be close to a hypernova. Again, just the right distance and just the right time in order to get the enrichment of everything we need. So it has to be a highly specialized star cluster in which we're born. Now, where do these star clusters actually exist? Well, there's one place in the universe, or in our galaxy, where these star clusters form, where you're going to have a sufficient density of these supernova, hypernova, and possible neutron star merging events. And so what astronomers have measured here is the abundance of elements heavier than helium relative to the distance from the center of our galaxy. The center of the galaxy is not the place with the highest density of heavy elements. It's about 4 kiloparsecs out from the center of our galaxy. And that dotted line that you see there, the longest dotted line, that shows you the place where our solar system formed. The second dotted line shows you where it is now. In order for us to be safe from these supernova eruption events today so that our civilization can survive, we must be at a spot in the galaxy where we're near a minimum abundance of heavy elements in the vicinity and at a minimum abundance of stars that are going to be radiating us with this energy. But this is something astronomers have discovered. We must have formed in the most dangerous part of our Milky Way galaxy and got kicked out and wound up being settled into the safest part of our Milky Way galaxy. And so this kind of shows you this is our Milky Way galaxy, the high accuracy map of our Milky Way galaxy, showing where the sun was and showing where the sun is now. You say, well, what is that red annulus? That red annulus represents what's called the corotation distance from the center of the galaxy. Because the farther away you are from the center of the galaxy, the longer it takes for a star to make an orbit about the center of the galaxy. But the spiral arm structure is rigid. And so we have this rigid rotating spiral arm disk, and we got the stars revolving at different rates depending how far they are from the center of the galaxy. That red annulus represents the distance from the center of our galaxy where a star orbits around the galaxy at the same rate that the spiral arm structure rotates. That's called the corotation distance, and that's the distance where you have the fewest spiral arm crossings. Now, if you're exactly at the corotation distance, you suffer from what's called a mean motion resonance, which means you're going to get kicked out. What happened is, and you say, well, how did this kick out happen? Okay, you're in this dense cluster in the most dangerous part of our galaxy, but if you get 4 or 5 supergiant stars in your vicinity, they can act as a gravitational trigger and basically kick your star with all of its planets out from that area. But in order to get it to stop, you need a second set of giant stars that causes a breaking of the system and causes it to settle down. Not a very high probability circumstance, but it literally took us from the most dangerous part to the safest spot and parked us just inside the co-rotation distance. When you're just inside, no mean motion resonance, but it also means you cross spiral arms very infrequently. Our sun crosses a spiral arm once every billion years. When you cross a spiral arm, really bad things happen. And we can see this in the fossil record, the mass extinction events that happen when you cross a spiral arm. Right now, we're halfway between the Perseus and Sagittarius spiral arms. We're at the safest time in the history of our sun's journey around the center of the galaxy. 500 million years from now, things are going to get nasty again. So you may want to take that into account in your investment strategies, that only for the next few million years are you going to be able to count on reasonably stable conditions. But here's the bottom line, before I open it up to Q&A. We live on a planet that's got 4 times as much phosphorus as what we'd expect for any other rocky planet in the universe. And phosphorus is a key constraint on how much life you can have on a planet. You've got strong teeth, well, you can thank the fact that we were close enough to an asymptotic giant branch star that our planet wound up with 50 times as much fluorine as what we'd expect for other rocky planets in the universe. And we got 60 times less sulfur. I was mentioning the Q&A on Thursday that Mars has got 60 times more sulfur than planet Earth does. And it's because Earth formed in a very different pathway than Mars did. And so we have 60 times less sulfur, which means we can grow potatoes on Earth. You cannot grow potatoes on Mars. You can't grow any vegetables on Mars. You can only do that on the Earth. 90 times as much potassium, and we have 1,200 times less carbon. Carbon is a very abundant element in the universe, so is nitrogen. But too much carbon would mean we would have a thick atmosphere of carbon monoxide and carbon dioxide. That would be suffocating for life. Same thing with nitrogen. We have 2,400 times less nitrogen. A large amount of nitrogen, it's not a greenhouse gas, but it enhances the effect of other greenhouse gases. And these are all vital poisons. Too much will kill you, too little will kill you. These are 6 of the 22 vital poisons. By the way, another vital poison is arsenic. That's one way to get rid of someone you don't like. Just, put a little bit of arsenic in their food. They won't notice it, but it'll kill them. But you need about 1 part per million arsenic in your body in order to live. And so you could literally die from being arsenic deficient. But it's easier to die from being arsenic overabundant. But it is a vital poison. Arsenic must be at just the right level. Okay, and then we have these other metals. They don't show up in our body, but they play crucial roles for our civilization. We live in an extremely aluminum-rich planet. We got 40 times as much aluminum, 65 times as much titanium. I don't know how many ever got here by airplane. We flew in an airplane to get here. Airplanes are possible because of the great abundance of aluminum and titanium on the crust of the Earth. The most extreme example would be uranium and thorium. We are literally living on the uranium-thorium champion of the universe. 610 times as much thorium as what we'd expect for any other rocky planet, and 340 times as much uranium. Most of that's in the interior of the Earth, and it provides a lot of the heat flowing out from the interior of the Earth that drives plate tectonics and establishes a strong magnetic field, which creates a magnetosphere around our planet that protects us from deadly solar radiation and deadly cosmic radiation, which is one reason why going to the moon is possible, but not going to Mars. Going to the moon, you're shielded by our Earth's magnetosphere for a good chunk of the way, and you don't have to spend a lot of time on the moon, so you can get back under that protective magnetosphere. That's not going to work if you try to go to Venus or Mars. You're going to be way outside that magnetosphere for far too long. And so next time you celebrate Thanksgiving, you might want to thank God for putting us on a planet with a superabundance of uranium and thorium. The book I got coming out in June or July, Designed to the Core, explains all the design that took place, the supernatural design that took place that caused our planet to be so super enriched with uranium and with thorium. And so again, if you want the free book, just take a picture with your smartphone of that QR code, and you'll be able to get that right away. I'm going to spend the rest of the time on questions, and I'll take questions on any subject that would be relevant to this conference. It doesn't have to be on nucleosynthesis. Yes, you're first.
Yeah, so I've got a couple questions. They're all kind of interconnected. First, to be honest, I haven't read any of your books yet. I've heard a couple of lectures. I've got some books, so it's on my reading list. So you've mentioned about 14 billion years. I'm curious, first part of the question, do you tend to lean more towards a theistic evolution type of approach? The second thing, kind of going through the creation story, let's say if you do, it seems to be that plants in a mature state, all that sort of stuff. The moon created a mature state. So if theistic evolution, how do you explain that connection? And then why, a lot of things I hear is, we see all these galaxies and things that are 50 million light years away, and the light has to travel here. Well, it kind of goes back to creating it in a mature state and understanding we have all these elements and everything, and kind of I guess I might challenge you on the kick-out thing from the Milky Way. Could not God have just put us in the right exact spot to say, look, all these things line up so perfectly because only I could do it. There was nothing else that had to happen.
Well, to deal with the last part of your question, I think God is the one that's responsible for that. Because from a naturalistic perspective, to have a planetary system form in the most dangerous part of our Milky Way galaxy, get enriched with exactly the right abundances of all these different elements that we need for our civilization, so billions of us could be redeemed from our sin, and then wind up settling in the safest part of our galaxy, that's beyond any naturalistic possibility. God is the one that made it all happen. Your first question, am I a theistic evolutionist? No. If you read my books, you'll see that I'm vigorously responding to the theistic evolutionists. I do believe that God creates instantaneously, but not all at the same time. It's millions of creation miracles stretched out over 6 long periods of time. As I read Genesis 1, it's clear to me that this word for day must have multiple literal definitions because multiple definitions are used right there on the first page. Creation day 1 is using the word day for the daylight hours. Creation day 4 uses the word day for 24 hours, and Genesis 2:4 uses the word day for the entirety of creation history. The reason I take the position that it's 6 consecutive long periods of time is that we see that there's no evening and morning for the 7th day. And the Hebrew words for evening and morning have 3 literal definitions each. We expect that because biblical Hebrew is a small vocabulary size. So virtually every noun has multiple literal definitions. But what's interesting about all 6 of the definitions for the Hebrew words for evening and morning, they imply that each creation day has a start time and an end time. The fact that we have no evening morning phrase for day 7 tells us we're still in God's 7th day. And what does the text tell us? For 6 days God creates, on the 7th day he stops. And part of my story is that I got studying astronomy since I was 7. I was reading multiple books a week on physics and astronomy, and my parents thought I was being a bit obsessive. And so when I was about 11, they bought our family this big, thick book on evolutionary biology. I was the only one in the family that read it, but I remember telling my parents the numbers don't add up. What you see before humanity is the sudden appearance of phyla, classes, and orders of life. What you see in the human era is none of that, which is consistent with for 6 days God creates on the 7th day rest. And very quickly, you spent a lot of time talking about the possibility that God creates with the appearance of age or with maturity. I would argue that God never does that. That when you look at the example of Adam and Eve, they did not come from the womb of a woman. Therefore, their height, it would not be an indicator of age. God instantaneously made Adam, but he made him fully functional. Because if he made him as a baby, his brain size would only be 1/3 of that of an adult. And God wanted rapid communication. And so creating Adam full size instantaneously without any appearance of age or maturation mean that he could begin a verbal conversation with him very quickly. With a baby, it takes 14, 18 months before they're verbally fluent. But if you have a full-size brain, that could happen very quickly. And when you look out at the universe, we don't see maturation. Rather, we see stars and galaxies. We see them of all different ages. Some we look at are brand new, just newly formed. Literally every day, we astronomers see stars that are just brand new formed, but we also see stars that are very old. So we see this whole panoply of ages that we measure, indicating that God was intervening multiple times throughout the entire history of the universe. And I think what's most significant, the Bible tells us God begins his works of redemption before he creates anything at all. And yeah, my next book, Design to the Core, basically makes the point. When you look at the whole history of the universe, every historical event for a galaxy, a star, a planet, life here on planet Earth, every component and every event plays a role in making possible the redemption of billions of human beings. You asked 5 questions, so that's why I had to take as long as I did. But over here.
On your last slide, I think there was a mistake. You said you're the champion, uranium, thorium champion, and yet your slide says 340.
Oh, that's a huge error. Thank you for correcting that. That's why I'm married to this woman. She's my editor. And I was rapidly putting this talk together. As I told you, it's based on some really new stuff. Yeah, that should be more, not less. We have 340 times more uranium and 610 times more thorium. So thank you. Yeah, your question.
I was wondering if you could expound a little bit on what a hypernova is and how it differs from supernova.
Okay, what does a hypernova differ from a supernova? Well, a star will go supernova if it has about 10 times the mass of our sun or the more. And the more massive the star, the greater the energy release in the supernova explosion. Hypernova are stars that are about 50 plus times the mass of our star, the sun. They're extremely rare. But when they do run through their nuclear fuel, they explode with at least 100 and more typically 1,000 times the energy release of a typical supernova. And it's because of that extraordinary energy release that you get molybdenum.
So were there more population 3 stars that were large enough to be hypernova?
That's what the James Webb Space Telescope is going to be commissioned to do, because we have seen the small population 3 stars because they take a long time to form. The problem is they're not pure hydrogen and helium because they actually get the ashes from nearby really big things. The bigger the star, the faster it goes through its burning cycle. And so the goal of the James Webb Space Telescope is to actually image the first of the population 3 stars, the stars that are nothing but hydrogen and helium and a tiny amount of lithium, no elements beyond that. And yes, the anticipation is those stars will be big. The reason why, it's rather challenging to have a star form where all you've got is hydrogen and helium in the gas mixture. And because you only have hydrogen and helium, that only permits the very largest stars to form. And the tiny population 3 stars we've seen basically took so long to form that they were polluted by the ashes of the really big population 3 stars. But yeah, the James Webb Space Telescope is going to nail all that down for us. It's the only telescope powerful enough to see the very firstborn stars. Our star is a population 1 star. You say, how come it all got mixed up like that? Well, astronomers could see the stars nearby first, and the nearby stars are all the late-born stars. They're the ones that are easy to see. The most difficult stars to see are going to be the population 3 stars. In fact, I remember as a graduate student, we hadn't seen any population 3 stars at all. The first one was discovered about a decade ago. Back here.
Dr. Ross, are we seeing any spectral lines that might indicate elements that are not on our Earth?
Yes, we do. We heard the question, do we actually see elements on other stars that are not here on planet Earth? Yes, the stars that are recently forming, when I was answering this gentleman's question, we actually do see stars that are just born. And those stars will have plutonium and neptunium. So that would be elements number 93 and 94. And the reason why we don't have any in our sun today, both neptunium and plutonium have half-lives of only a few million years. And since our solar system is about 4.5 billion years old, that stuff is completely decayed away. Incidentally, we do know plutonium and neptunium were here on the Earth because we see the decay daughter products of those radioactive elements in the crust of the Earth. And so that's proof that plutonium was here. but there's none to be found because it's completely decayed away. But yeah, and also you'll see elements like californium in these newborn stars. So the actinium elements are present, but they decay even more rapidly than plutonium and neptunium. Yes?
So speaking of the James Webb Telescope, I believe you said yesterday that you were going to use it to view the stars that originally
Right.
long ago. I've heard that our observable universe is somewhere around 93 billion.
Well, that's how big the observable universe is today. It's about 93 billion light years across. The universe we see through the telescope is the universe of the past. And so the farther away you look, the farther back in time you're seeing, because it takes light time to travel to us. But the farther away you look, the smaller the universe is. So the universe we see through our telescope is about 13.8 billion years in terms of its radius.
So is that what we see through the telescopes? Is that part of the observable universe?
What we see through the telescope is the universe of the past. I mean, I joke with my wife that since I'm an astronomer, I can't be held for anything happening in the present because all of my data comes from the past. But the wonderful thing about the time in which we live in this universe is that if God had put us here 5 billion years earlier, light from the cosmic creation event wouldn't have time to travel along the space surface of the universe and reach our telescopes. We would never be able to witness the cosmic creation event. And if you put us here 5 billion years in the future, dark energy would be expanding the universe at greater than the velocity of light. Likewise, you wouldn't see the light from the cosmic creation event. We were here at that one time in cosmic history when we can look through our telescopes all the way back and directly witness God creating the universe. Now, I often get accused of that being an exaggeration. It's a tiny exaggeration. The closest we can get to the cosmic creation event is 100 billionth of a trillionth of a trillionth of a second after the universe was created. So we can get really close. And it's that capacity that gives us the most compelling evidence that a God beyond space and time must have created the universe. God wanted us to read the book.
So when we point the telescope in a certain direction, how do you know that that's the correct direction?
Well, in terms of looking back to the cosmic creation event, it doesn't matter where you look. Everywhere you look is going to take you back to the cosmic creation event because the universe begins infinitesimally small and then it expands and becomes bigger and bigger. So no matter where you are on the space surface of the universe, if you look 13.8 billion years away, you're looking back to that time when it was an infinitesimal volume.
Okay. And if I may ask another one. So earlier you talked about the universe having the correct amount of mass to create the correct amount of elements to
Right.
create life in the universe. Do you believe that there are other universes that, like, do you believe in multiverse that might have been created that do not have, or that had different amounts of mass that created different amounts of elements?
Well, the correct answer to that would be, I don't know. And the reason why is we see that the universe is governed by Einstein's theory of general relativity. And one of the implications of general relativity is observers within universe A can only observe universe A. If God made another one, none of our telescopes can access that. On the other hand, we do know that an inflation event happened when the universe was 10 to the minus 35 seconds old. That inflation event will make other space-time realms, but they're completely inaccessible to us today. And incidentally, from the Bible's perspective, we do know that God made other dimensional realms. He's got a separate one for the angels. There's heaven, there's hell. Those are all distinct from the space-time dimensions of our universe. But exactly how many God made, we don't know.
So speaking of the theory of relativity, do you have a theory that combines the theory of relativity and string theory?
Yes, you'll see it in Beyond the Cosmos, chapter 3. But what I talk about are the discoveries by some friends of mine at Caltech that basically established we live in a universe with 9 dimensions of space, where you got 9 dimensions rapidly expanding from the cosmic creation event. But when gravity separates out from the other 3 forces of physics, 6 of those 9 dimensions stop expanding. What my friends at Caltech discovered, if all you got are 3 big dimensions of space, you cannot integrate a particle creation model with a cosmic creation model. You need more dimensional room. And it took them a decade to figure out that it needed 6 other dimensions of space. Now, that does accommodate string theory, but string theory is only one set of theories that explains how we can seamlessly integrate our cosmic creation model with our particle creation model. There are other models that compete with string theory, but they all require these 6 tiny dimensions to accommodate the 3 big ones. By the way, those 9 dimensions are still here today. The 6 small ones are wrapped very tightly around the 3 big ones. The reason you don't notice them, the cross-section measures 10 billion trillion times smaller than the diameter of an electron. So that's why people didn't really pay much attention to it until fairly recently. Okay, over here. And someone's got to watch the clock. I can't really see the clock that well from here, so let me know when I'm out of time.
So these 3 kind of deal with like witnessing, not so much on the scientific base. Growing up, we were always taught that like Big Bang wasn't part of the Christian worldview, that we never considered it. Lately, reading like Frank Turek's book with Norman Geisler, I don't have enough faith to be an atheist. With the cosmological and the fine-tuning argument. How do we help, I guess what's the best way? Because I've tried to share with my preacher, just a lot of different people that I guess haven't considered it. How do we help them with it?
Okay, we're running out of time, so I'm going to very quickly cut in here. Okay, when Big Bang cosmology was first proposed in 1925, astronomers who were atheists strongly reacted against it. Why? Because they saw it as a biblical Christian model. So they said, we got to find some other way to explain the universe other than Big Bang cosmology. It explains why they propose a steady state theory, the oscillating universe theory, and other theories. Today, the evidence from astronomical observations is overwhelming. There is no reason for doubting Big Bang cosmology. And yes, the Bible said it first. And you can go on our reasons.org website. I've got a weekly blog called Today's New Reason to Believe. And one of those articles is actually titled, Big Bang, the Bible Said It First. And the other one actually makes the point, this isn't hindsight. Jewish theologians living 800, 900, 1100 years ago, reading the Old Testament, saw these same Big Bang features recorded in the Scripture. And the Bible is alone amongst the world's holy books in actually predicting that we live in a Big Bang universe. Thank you.